My name is Philip Drake and I'm a senior in computer science. Self-assembling structures are structures which automatically coalesce together to form more complex objects by simple rules that denote what binds to each other. This could be seen as analogous to DNA, which binds together on certain base pairs. A goes to T and C goes to G. And certain strings of base pairs only bind to certain other strings of base pairs, their complement. We use an abstraction of that rule, specifically by abstracting those to tiles which bind together, or slabs which bind together, and test to see the computational complexity and capabilities of those models. The hardest part of this is definitely the visualization of the system that you're trying to build. When structures self-assemble, they are inherently geometric, where certain blocks have to come in after other blocks, and they could block each other's growth, or maybe that block is what you need to have correct growth. And there are thousands of states that you have to account for at any given point in time. It's very difficult to understand that how to best design your system such that it both minimizes those number of errant states that you could be in, and that every state that it could be in is valid to complete your computation. The favorite part of the work that I'm doing right now has to be the creative aspect, looking at specific end state that you want to have, a specific algorithm that you want to compute, or a specific shape that you want to build, and thinking of how can I implement this in the way that's most efficient possible. Ultimately, we are looking at models of DNA computation, and DNA, as you can imagine, is very, very small, and it's a natural substance, so it's easily able to be put into a human body. So if we're able to have DNA computations that work out, they can be used for experimental remedies, which can be used to treat a wide variety of diseases and ailments. It can be injected into the human body, and the DNA, it's able to autonomously compute in such a way that it knows that it's hitting a certain bad cell or a certain bad actor, and put an end to that. Before working on this project or any other projects in this lab, I knew absolutely nothing about DNA computing or even how DNA really works in the body. And I've had the opportunity to not just create models for what DNA computation would look like, but also design DNA systems which are able to self-assemble in the test tube. And I've been able to image them in a laboratory in Maynooth. And the opportunity to do that was amazing, and I gained an elementary knowledge of basically every tool that you need to use in the lab in order to make that happen. Midway through my junior year of college, I went to a professor talk hosted by ACM. And at that talk, the professor that I'm working with, Dr. Patitz, he gave a short talk about the research that he's doing in tile assembly and how that relates to DNA assembly. And I told myself that I would not be happy doing research with anyone else unless it was in his field of research. It was just an immediate interest that I had in the way that these simple building blocks are able to assemble to make more complicated structures. And so I went to an interest meeting hosted by him where he gave out a worksheet for us to fill out, just to show that we're interested and capable of working with the models. And after probably weeks of working on that worksheet, I gave it to him, and he liked my submission and he took me onto the team. The coolest part is definitely going to the lab in Maynooth, Ireland, and actually seeing the structures assemble. When you work on it on a computer, it's a lot more abstract. To see that this could actually be implemented, and it was amazing to be able to image the DNA that was assembled to form the structure that I had put together beforehand, and it was very formative in my understanding of what this field is and how it is important. At this moment in time, there is no realized model of what is called a Turing machine out of DNA, and a Turing machine is effectively the very most basic formalized model of a computer and the way that any given algorithm is able to be done. We have some innovations in the lab which are making the ability to actually create a Turing machine out of DNA much more realizable than it has been before. We have techniques that have reduced error reduction by orders of magnitude compared to what they were before. This could be used to generate that very interesting model. Our lab is always looking for more people. If you are at all interested in this research, contact Dr. Patitz. It's at patitz@uark.edu or Dr. Trent Rogers at tar003@uark.edu. Either of those people are going to be able to help you get involved, and I guarantee that we would be interested in your outlook.